Just like we have definition of real valued functions, we also have the concept of derivative of complex functions. If limit delta z tends to 0, f of z plus delta z minus f of z upon delta z exists. That is, if this particular limit remains to be unique, whichever path along which delta z approaches 0, then we say that the function f of z is derivable, or the derivative of f of z exists. We have the notation for derivative of f of z as f dash of z or dw by dz, because we have assumed w equals f of z. Moving on to the definition of analytic function, which is also known as regular function or holomorphic function. A single valued function f of z, if it possesses unique derivative at all points in the region R considered, then we say that the function f of z is analytic in the region R. Why is an analytic function also known as a regular function? Because it also involves the concept of regular point. When do we say that z0, a complex number, is a regular point? If there exists a disk centered at z0 of radius delta, where delta is a considerably small positive real number, that is, you are considering a disk of points lying in the close neighborhood of z0, and if f of z is differentiable not only at z0 but also at every point in the neighborhood of z0, then we say that z0 is a regular point. And if in the domain considered every z0 or every arbitrary complex number z happens to be a regular function, then we say that f of z is an analytic function in that domain. The concept of differentiability of f of z and analyticity of f of z is quite different. Differentiability is with respect to a point z0, and analyticity is with respect to a collection of points lying in the neighborhood of z0. An entire function is a complex function which is analytic everywhere in the complex plane. An example for entire function is polynomial functions defined in terms of complex variable. Moving on to Cauchy-Riemann equations. Cauchy-Riemann equations are necessary and sufficient condition for a function f of z to be analytic. Suppose f of z is a complex function and the partial derivatives dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y are continuous functions of x and y, where u of xy and v of xy are real valued function, and we have the representation f of z equals u of xy plus I times v of xy. Also, we have the partial derivatives of u and v satisfying the relation dou u by dou x equals dou v by dou y, and dou u by dou y equals minus of dou v by dou x. Then we say that the given function f of z is analytic. The second condition is known as Cauchy-Riemann equation. These two equations are together known as Cauchy-Riemann equations. So if we wish to check whether f of z is analytic, we have to check whether these partial derivatives exist and they are continuous. Also, we have to check whether the Cauchy-Riemann equations are satisfied. For example, consider a function f of z equal to z square. If we wish to check whether f of z is analytic, then we have to check whether the partial derivatives are continuous and the partial derivatives satisfy the Cauchy-Riemann equations. Here we have z square equals x plus iy the whole square, which can be written as x square plus 2xy into I minus y square. We separate real and imaginary parts, and we have real part is x square minus y square and imaginary part is 2xy. We take the partial derivatives of u with respect to x and y, which gives us ux and uy, which are dou u by dou x and dou u by dou y respectively. Similarly, we evaluate vx and vy. Here we see that all the partial derivatives are well defined and are continuous functions. Hence, we check for the CR equations. Here we can also see that the CR equations are satisfied, that is ux equals vy and uy equals minus of vx is satisfied, and hence we conclude that f of z is analytic function.